Welcome to Tech with Kaushik. This is set 11 of our DOP-C02 AWS Certified DevOps Engineer Professional Practice Question Series. Choose your answer before the timer ends. Then review the correct answer, detailed explanation, and exam tip. Keep track of your score and see how exam ready you are. Each practice set is completely standalone, so you can start here without watching any of the other sets first. Playlist link in the description. Let us begin set 11. Question number 187. The topic for this question is AWS Config Auto Remediation. A technology company requires VPC flow logs to be enabled for all Amazon VPCs across its central networking account. Currently, the infrastructure team provisions VPCs via AWS CloudFormation. However, various IAM users have permissions to create VPCs manually for sandbox testing. The security team needs a solution that guarantees VPC flow logs are configured for every existing VPC and any new VPC that is created in the account, regardless of whether the VPC was created by CloudFormation, the AWS Management Console, or the AWS CLI. Which solution satisfies this requirement across all provisioning methods? Options. Option A. Enable AWS config and deploy the VPC flow logs enabled managed rule. Configure an AWS config automatic remediation action utilizing an AWS Systems Manager automation runbook to enable flow logs on non-compliant VPCs. Option B. Create an organization using AWS South organizations and place the networking account inside it. Apply a service control policy, SCP, to the account that explicitly denies the EC2, delete flow logs, and EC2, modify flow logs API actions for all IAM users. Option C. Create an identity-based IAM policy that explicitly denies the EC2. Create VPC API action unless the request also includes parameters to configure a VPC flow log. Attach this policy to all IAM users and roles in the account. Option D. Update the central AWS CloudFormation templates to include the AWS EC2 flow log resource alongside every AWS EC2 VPC resource and restrict IAM users to only deploying VPCs via CloudFormation. In this case, choose option A. Enable AWS config and deploy the VPC flow logs enabled managed rule. Configure an AWS config automatic remediation action utilizing an AWS Systems Manager automation runbook to enable flow logs on non-compliant VPCs. Let's look at the reasoning. The requirement dictates that VPC flow logs must be enforced regardless of how the VPC is created, CloudFormation, Console, CLI. AWS config provides continuous detective compliance across the account. The VPC flow logs enabled managed rule detects VPCs without flow logs, and AWS config automatic remediation, backed by Systems Manager automation, can programmatically remediate the violation by enabling the flow logs immediately after detection. The other choices do not work because B. An SCP can prevent users from deleting existing flow logs, but it cannot actively create flow logs for newly provisioned VPCs. C. IAM policies cannot easily enforce complex conditional logic requiring multiple distinct API parameters during VPC creation, making this approach brittle and impractical for enforcing flow log creation. D. Updating CloudFormation templates only secures VPCs created via infrastructure as code. It fails to address VPCs created manually via the console or CLI. Keep this point in mind for the exam. When a requirement asks to ensure a configuration state, like flow logs or encryption, for all resources regardless of how they are provisioned, look for AWS config paired with automatic remediation. Question number 188. Let's go. Scenario. A software vendor operates an organization in AWS organizations containing multiple AWS accounts. Software engineering teams manage their code using AWS code commit repositories scattered across these accounts. Engineers authenticate using AWS IAM Identity Center integrated with an external identity provider, IDP. All engineering teams receive the same developer permission set, which grants basic Git access to code commit. A recent security review found that because the base permissions are the same, any engineer can modify the main branch of repositories owned by other teams. The DevOps team must implement a solution that restricts engineers to modifying the main branch of only the repositories owned by their specific engineering team. Which combination of steps will enforce this access control utilizing attribute-based access control, ABAC? Choose 3. Choose every option that satisfies the requirement. Option A. Configure IAM Identity Center attributes for access control so the external IDP team attribute is passed into AWS sessions as the access team session tag, available as AWS principal tag/access team. Option B. Tag every code commit repository with a resource tag named access team whose value identifies the owning engineering team. Option C. Update the IAM Identity Center permission set policy used by developers so changes to refs/head/main are denied when AWS resource tag/access team does not match $AWS principal tag/access team. Use the code commit references condition for branch scoped git push and merge actions, including the required null handling for git push. Option D. Create an approval rule template and use the AWS principal tag/access team value as a pull request approval requirement without changing IAM authorization for git pushes. Option E. Attach a permissions boundary that restricts only code commit, git push by repository tags, but leaves all merge actions to main unrestricted. Option F. Require signed commits whose signer email address matches the email address supplied by the external IDP. You should choose option A. Configure IAM Identity Center attributes for access control so the external IDP team attribute is passed into AWS sessions as the access team session tag, available as AWS principal tag/access team. Option B. Tag every code commit repository with a resource tag named access team whose value identifies the owning engineering team. And option C. Update the IAM Identity Center permission set policy used by developers so changes to refs/heads/main are denied when AWS resource tag/access team does not match $AWS principal tag/access team. Use the code commit references condition for branch scoped git push and merge actions, including the required null handling for git push. ABAC requires attributes on the principal, matching tags on the resource, and an authorization policy that compares them. IAM Identity Center can pass external IDP attributes as session tags. Code commit repository tags are available through AWS resource tag, and code commit supports branch restrictions with code commit references. Together, A, B, and C restrict main branch changes to repositories whose team tag matches the developer session tag. D. Approval rules govern pull request approvals. They do not prevent direct git pushes or all merge paths by team tag. E. Restricting only git push leaves merge AP is capable of modifying main, so it does not meet the stated requirement. F. Signed commits establish commit authenticity, not repository-level ABAC authorization based on team ownership. Exam tip. IAM Identity Center ABAC uses session tags as AWS principal tag values, combine them with resource tags, and use service-specific condition keys such as code commit references when the policy must also be branch-aware. Next, question number 189. The focus now shifts to AWS WAF logging architecture. A retail company defends its customer-facing web applications using AWS WAF. A dedicated Security Operations Center, SOC, needs the ability to continuously analyze AWS WAF log messages. Furthermore, the SOC engineers must be able to configure automated alarms that trigger whenever specific attack patterns, such as repeated SQL injection attempts, appear in the WAF logs. Which architecture meets these requirements with the least operational overhead? Choices. Option A. Create an Amazon Cloud Watchlogs log group. Configure the AWS WAF Web ACL to output logs directly to this log group. Instruct the SOC engineers to create CloudWatch logs metric filters for their desired patterns and set CloudWatch alarms on those metrics. Option B. Create an Amazon S3 bucket. Configure AWS WAF to output logs to the bucket. Use Amazon Athena to define an external table for the logs. Have the SOC write scheduled SQL queries in Athena that publish results as custom CloudWatch metrics. Option C. Deploy an Amazon OpenSearch Service cluster. Configure AWS WAF to send logs via Amazon Kinesis data firehose to the OpenSearch index. Instruct the SOC engineers to use OpenSearch dashboards to build alerting rules for the specific attack patterns. Option D. Create an Amazon S3 bucket. Configure AWS WAF to deliver logs to the S3 bucket. Deploy an AWS Lambda function triggered by S3. Object-created events to parse the logs for attack patterns and directly publish matching events to an Amazon SNS topic. The best choice is option A. Create an Amazon Cloud Watch Logs log group. Configure the AWS WAF Web ACL to output logs directly to this log group. Instruct the SOC engineers to create CloudWatch Logs metric filters for their desired patterns and set CloudWatch alarms on those metrics. Here's why. AWS WAF supports direct logging to Amazon CloudWatch Logs. Once logs are flowing into a CloudWatch log group, CloudWatch metric filters can be natively configured to search for specific text patterns, like SQL injection signatures, in real time. These filters increment custom CloudWatch metrics, which can then seamlessly trigger CloudWatch alarms. This provides a fully managed, serverless alerting pipeline with minimal setup and zero maintenance. The remaining options can be eliminated because B. Athena is excellent for ad hoc querying of S3 data, but writing scheduled SQL queries to emit custom metrics is complex, delayed, and operationally heavy compared to native metric filters. C. OpenSearch is a powerful search and analytics engine, but deploying and managing an OpenSearch cluster incurs significant operational overhead and cost when native CloudWatch alarms satisfy the requirement. D. Writing custom Lambda functions to parse raw logs in S3 and trigger SNS introduces unnecessary coding, maintenance, and potential scaling bottlenecks. The main takeaway is for the least operational overhead when filtering text logs to trigger immediate alarms. Always choose CloudWatch logs paired with metric filters and CloudWatch alarms. Question number 190. Here's the scenario. A manufacturing company governs its AWS environment using an AWS control tower landing zone. The organization's hierarchy includes a workloads OU. Nested directly underneath the workloads OU are two child OUs, a development OU and a production OU. Developers are granted broad administrative access to the AWS accounts within these OUs to rapidly deploy and test applications. However, the security team wants to enforce a strict boundary. Inside the accounts located in the production OU only, no one is allowed to create, modify, or delete IAM roles and policies, except for a dedicated automated IAM role named Security Admin Role. Which SCP design implements this restriction accurately? Option A. Create an SCP that denies IAM role and policy administration when AWS Principal ARN does not match the Security Admin Role ARN. Attach the SCP only to the production OU. Option B. Create the same exception-based deny SCP, but attach it to the parent workloads OU. Option C. Create an SCP with an allow for IAM administration and attach it only to the development OU. Option D. Create an SCP that denies all AWS actions except when the principal is Security Admin Role and attach it at the organization root. The answer here is option A. Create an SCP that denies IAM role and policy administration when AWS Principal ARN does not match the Security Admin Role ARN. Attach the SCP only to the production OU. This is the best choice because an explicit deny SCP attached only to the production OU creates the required organization-level boundary for production accounts. A condition that exempts the Security Admin Role leaves that role outside the deny while all other principals in those accounts remain blocked from the specified IAM administration actions. Let's quickly check the incorrect choices. B. Attaching the deny to workloads would also restrict the development OU. C. An allow SCP on development does not create the required deny boundary in production and SCPs do not grant identity permissions. D. A root-level deny of all other AWS actions would affect the entire organization and is far broader than the requirement. Place an exception-based deny SCP at the narrowest OU that must be protected. Use AWS Principal ARN conditions to exempt only the designated administrative role. Next, question number 191. Scenario. A DevOps engineer is developing an asynchronous data processing pipeline. The architecture uses an Amazon SQS standard queue as an event source for an AWS Lambda function. The Lambda function processes incoming messages in batches and writes the extracted content to an Amazon DynamoDB table. During load testing, the engineer notices that if a single message in a batch causes the Lambda function to throw an error, the entire batch is returned to the SQS. This causes successfully processed messages in the same batch to be reprocessed, resulting in redundant DynamoDB writes. The engineer must prevent successfully processed messages from being reprocessed, while ensuring maximum throughput and scalability. Which configuration adjustment should the engineer make? Choices. Option A. Include the report batch item failures value in the function response types list within the Lambda function's SQS event source mapping, and return the IDs of the failed messages in the function payload. Option B. Reduce the batch size parameter in the Lambda function's event source mapping to 1, forcing Lambda to process messages individually. Option C. Configure the Lambda function's event source mapping to use a batch window of 0 seconds so that messages are delivered immediately without grouping. Option D. Increase the SQS visibility timeout to perfectly match the Lambda function's execution timeout to prevent invocation throttling and retry storms. Go with Option A. Include the report batch item failures value in the function response types list within the Lambda function's SQS event source mapping, and return the IDs of the failed messages in the function payload. This works because by default, if an AWS Lambda function processing an Amazon SQS batch throws an error, the entire batch of messages is returned to the queue and becomes visible again. To prevent reprocessing of successfully processed messages while maximizing batch efficiency, you must enable report batch item failures in the event source mapping. The Lambda function must then be updated to catch errors internally and return a JSON payload containing only the message IDs of the specific messages that failed. SQS will only retry those specific failed messages. Now let's rule out the other options. B. Reducing the batch size to 1 eliminates batch reprocessing, but severely impacts throughput and scalability, violating the maximum scalability requirement. C. Changing the batch window to 0 seconds does not solve the batch failure behavior. It only instructs Lambda to invoke immediately without waiting to group more messages. D. Modifying the visibility timeout ensures Lambda has enough time to process messages before they reappear on the queue, but it does not prevent the entire batch from being retried if a single internal failure occurs. A helpful shortcut is this. To achieve partial batch success with SQS and Lambda without duplicating effort, always configure report batch item failures and return the failed message IDs. Question number 192. Let's go. This is a medium-level challenge. Scenario. A company runs a critical .NET application on a fleet of Windows-based Amazon EC2 instances. The company uses AWS Directory Service for Microsoft Active Directory, AWS Managed Microsoft AD, for centralized authentication. A cloud engineer is designing an AWS CloudFormation template to deploy this architecture. The template provisions an auto-scaling group, an EC2 launch template, security groups, and an IAM role for the instances. The engineer must ensure that all newly launched EC2 instances automatically join the existing AWS Managed Microsoft AD domain upon boot. Which approach fulfills this requirement with the most operational efficiency? Options. Option A. Update the CloudFormation launch template to tag the instances appropriately. Use an AWS hesitant face SM association resource in the template to associate the AWS managed AWS Join Directory Service Domain Systems Manager document with instances bearing those tags, providing the directory parameters. Ensure the instance IAM role includes Amazon SSM Directory Service Access and Amazon SSM Managed Instance Core. Option B. Store the AD administrator password in AWS Secrets Manager. Update the EC2 launch template's user data script to retrieve the credential using the AWS CLI and execute a PowerShell script to join the domain natively. Ensure the instance IAM role includes Secrets Manager read-write. Option C. Create a custom AWS hesitant face SM document resource in the CloudFormation template containing PowerShell scripts to join the domain. Update the EC2 launch template to utilize the SSM association property to bind this document to the instances on boot. Option D. Place the domain connection parameters in AWS Secrets Manager. Use an AWS hesitant face SM association in the CloudFormation template to associate the AWS Create Managed Windows instance with Approval Runbook with the auto-scaling group directly, referencing the Secrets Manager ARNs. The right response is Option A. Update the CloudFormation launch template to tag the instances appropriately. Use an AWS hesitant face SM association resource in the template to associate the AWS-managed AWS Join Directory Service Domain Systems Manager document with instances bearing those tags, providing the directory parameters. Ensure the instance IAM role includes Amazon SSM Directory Service Access and Amazon SSM Managed Instance Core. The main reason is AWS Systems Manager provides a native, managed method for seamless Active Directory domain joins. The AWS Join Directory Service Domain SSM document automatically handles joining a Windows instance to an AWS-managed Microsoft AD domain. The most operationally efficient CloudFormation strategy is to tag the auto-scaling group instances and use an AWS hesitant face SM association to automatically apply the document to instances matching those tags upon boot. The IAM role must include permissions to communicate with SSM and directory service. Here's why the alternatives are not suitable. B. Storing AD credentials in Secrets Manager and writing custom PowerShell logic and user data introduces operational overhead for credential rotation and custom script maintenance. C. Creating a custom AWS hesitant face SM document with manual PowerShell scripts ignores the heavily tested AWS-managed AWS Join Directory Service Domain document. Additionally, SSM association is not a valid EC2 launch template property. D. The AWS Create Managed Windows Instance with Approval Runbook is designed for standalone instance provisioning workflows, not for joining instances launched dynamically via auto-scaling groups. Here's a useful exam tip. For seamless Windows domain join automation without custom scripts, utilize the AWS-managed AWS Join Directory Service Domain SSM document applied via State Manager Associations, tag-based. Question number 193. A logistics company operates a Tier 1 application actively deployed across 2 AWS regions to ensure high availability. Each region serves traffic through an application load balancer, ALB. The global DNS routing is managed using Amazon Route 53 alias records. To manage controlled failover between the two regions, the company uses Amazon Route 53 Application Recovery Controller, ARC. A routing control has been established for both the primary and secondary regions. During a recent simulated disaster recovery exercise, an operator mistakenly toggled both routing controls to the off state simultaneously, effectively blackholing all application traffic globally. The company must implement a safeguard to prevent both routing controls from being disabled at the same time. Which Route 53 ARC feature resolves this issue? Option A. Create an assertion safety rule in Route 53 ARC applied to both routing controls. Configure the rule type as at least with a threshold of 1. Option B. Create a gating safety rule in Route 53 ARC applied to both routing controls. Configure the rule type as or with a threshold of 1. Option C. Create a new Route 53 ARC resource set with an AWS Route 53 health check resource type targeting the routing control ARNs. Attach a readiness check to this resource set. Option D. Create a new Route 53 ARC resource set with an AWS Route 53 recovery readiness. DNS target resource type targeting the alias domain names. Attach a readiness check to enforce routing state. In this case, choose option A. Create an assertion safety rule in Route 53 ARC applied to both routing controls. Configure the rule type as at least with a threshold of 1. Let's look at the reasoning. Amazon Route 53 Application Recovery Controller, ARC, includes a safety rules feature designed specifically to prevent operator errors from causing catastrophic outages. An assertion safety rule enforces a specific state invariant. By setting an assertion rule to type at least with a threshold of 1 across both routing controls, Route 53 ARC strictly guarantees that at least one routing control is always in the on state. If an operator attempts to turn off the final remaining active control, ARC will reject the API request. The other choices do not work because B, a gating rule, evaluates gating controls, like an overarching on-off switch for maintenance, before allowing state changes to underlying controls. It is not used to enforce a minimum number of active controls. C. Route 53 health checks and readiness checks evaluate the underlying health of resources, but they do not actively prevent an operator from toggling routing controls off. D. Readiness checks verify the capacity and configuration of disaster recovery environments. They do not enforce ARC routing control states. Keep this point in mind for the exam. To prevent fat finger errors where all traffic is accidentally blackholed during manual arc failover, use an assertion safety rule with an at least threshold of 1. Now for question number 194. This one is marked hard. Eliminate the options systematically. Here's what is happening. An enterprise has deployed a centralized multi-account environment using AWS Control Tower. The cloud engineering team has built the fundamental organizational unit, OU, structure, and established dedicated core accounts for networking, security, and logging. The enterprise wants to provide internal application teams with a self-service catalog of approved infrastructure customizations. Teams should be able to request and provision these customizations into their respective AWS accounts directly through the AWS Control Tower Account Factory interface. Which combination of steps is required to offer these customizations via Control Tower? Choose 3. Select all answers that apply. The choices are: Choice A, create an AWS Service Catalog product for each CloudFormation template representing a customization. Choice B, create an IAM role named AWS Control Tower Blueprint Access in the Hub account. Configure the role's trust policy to allow the AWS Control Tower admin role to assume it, and attach the AWS Service Catalog admin full access manage policy. Choice C, author an AWS CloudFormation template that defines the infrastructure resources for each individual customization. Choice D, deploy the customizations for AWS Control Tower, CFCT, CloudFormation stack in the management account to orchestrate the service catalog portfolios. Choice E, create an AWS CloudFormation stack set for each CloudFormation template. Enable automatic deployment on the stack set and create stack instances targeting the specific application OUs. Choice F, enable trusted access for AWS CloudFormation within AWS organizations using service managed permissions in the management account. The required selections are Option A, create an AWS Service Catalog product for each CloudFormation template representing a customization. Option B, create an IAM role named AWS Control Tower Blueprint Access in the Hub account. Configure the role's trust policy to allow the AWS Control Tower admin role to assume it, and attach the AWS Service Catalog admin full access managed policy. And Option C, author an AWS CloudFormation template that defines the infrastructure resources for each individual customization. AWS Control Tower Account Factory allows provisioning of standardized accounts. To offer infrastructure customizations, Account Factory customizations, AFC, the workflow relies on AWS Service Catalog. The required steps are: define the infrastructure customization using an AWS CloudFormation template. Publish that template as an AWS Service Catalog product. Establish trust between Control Tower and Service Catalog by creating the specific AWS Control Tower Blueprint Access IAM role, which allows Control Tower to read and deploy the Service Catalog blueprints. D. Customizations for AWS Control Tower, CFCT, is a separate, advanced framework utilizing code pipeline and stack sets for lifecycle event automation. The scenario specifically asks to offer customizations requested through the AWS Control Tower Account Factory interface, which uses Account Factory customizations, AFC, not CFCT. E. While CloudFormation stack sets can deploy across OUs, they do not integrate directly into the self-service Control Tower Account Factory UI workflow for users. F. Service managed permissions for CloudFormation stack sets are unrelated to publishing Service Catalog blueprints for Account Factory customizations. Exam tip: Account Factory customizations, AFC, in Control Tower require turning CloudFormation templates into Service Catalog products and configuring the AWS Control Tower Blueprint Access IAM role. Question number 195. Let's go. A DevOps engineer maintains a CloudFormation managed fleet of legacy Linux EC2 instances. Application dependencies are installed by a shell script in EC2 user data. The instances are already registered as AWS Systems Manager managed nodes, and their instance profile includes Amazon SSM Managed Instance Core. The engineer changed the installation script in the CloudFormation template, but the already running application instances did not execute the new script. The engineer must apply the updated configuration to the existing instances without stopping, rebooting, or replacing them, and should use the managed configuration capability already available on the fleet. Which combination of steps will accomplish this with the most operational efficiency? Choose 2. More than one answer may be correct. Options. Option A. Refactor the application installation commands to use an AWS Systems Manager (SSM) document instead of EC2 user data. Option B. Use AWS Systems Manager State Manager to create an association between the newly created SSM document and the targeted EC2 instances. Option C. Refactor the user data block to use the CFN init and CFN hub helper scripts to monitor CloudFormation metadata changes and apply updates locally. Option D. Update the CloudFormation template to place the instances in an EC2 auto-scaling group and apply an auto-scaling scheduled action update policy. Option E. Modify the user data content to use the MIME multi-part format and set the script's user directive to always in the text/cloud config section. The answers that work here are Option A. Refactor the application installation commands to use an AWS Systems Manager (SSM) document instead of EC2 user data, and Option B. Use AWS Systems Manager State Manager to create an association between the newly created SSM document and the targeted EC2 instances. Here's why. EC2 user data is normally processed during instance boot, and changing the user data property does not by itself rerun the new commands on already running instances. Because the fleet is already managed by Systems Manager, moving the commands into an SSM document and associating that document with the targets through State Manager applies the desired configuration in place without a reboot or instance replacement. The remaining options can be eliminated because CFN hub can react to CloudFormation metadata changes only after it has been installed and configured on the instances. The existing fleet was not set up for that mechanism. D. Moving the application into an auto-scaling group and using an update policy changes the deployment model and can replace instances, contrary to the requirement. E. Configuring Cloud Init to run user data on every boot still requires a reboot to execute the changed user data, which the scenario forbids. The main takeaway is for ongoing desired state changes on already running managed nodes, use Systems Manager State Manager and SSM documents instead of relying on EC2 user data reruns. Question number 196. Next, let's move into Control Tower, or DS alerts. Scenario. A healthcare provider operates a multi-account environment governed by AWS Control Tower, complete with a central audit account. To meet strict HIPAA compliance requirements, every Amazon RDS database across all member accounts must have storage encryption enabled at rest. The security operations team needs an automated alerting mechanism that immediately notifies them via email if any non-compliant, unencrypted RDS database is detected anywhere in the organization. Which solution satisfies this requirement with the most operational efficiency? Option A. Enable the AWS Control Tower Detective Control that checks whether RDS DB instances have storage encryption enabled on the required OUs. In the audit account, subscribe the security team email to the AWS Control Tower Aggregate Security Notifications (SNS) topic that receives forwarded AWS config compliance change notifications. Option B. Deploy an AWS CloudFormation stack set to distribute an AWS Lambda function to every member account. Write the Lambda function to scan for unencrypted RDS databases and push a custom metric to CloudWatch in the management account. Create a CloudWatch alarm in the management account that triggers an Amazon SNS email notification when the metric rises. Option C. Manually deploy a custom AWS config rule into every member account to evaluate RDS encryption status. In the central audit account, create an Amazon SNS topic for email notifications. Create an Amazon Event Bridge rule to capture the local config compliance change events and route them to the SNS topic. Option D. Provision an Amazon EC2 instance in the audit account. Schedule a cron job to assume cross-account IAM roles and run AWS CLI scripts against all member accounts hourly to check RDS encryption status. Configure the instance to send emails via Amazon SES when non-compliant resources are discovered. Go with Option A. Enable the AWS Control Tower Detective Control that checks whether RDS DB instances have storage encryption enabled on the required OUs. In the audit account, subscribe the security team email to the AWS Control Tower Aggregate Security Notifications (SNS) topic that receives forwarded AWS config compliance change notifications. This is the best choice because Control Tower detective controls are implemented with AWS config rules, and Control Tower centralizes control compliance notifications in SNS topics in the audit account. The aggregate security notifications topic receives forwarded regional compliance changes, so subscribing the security team provides a managed organization-wide email path without custom scanning code. Let's quickly check the incorrect choices. B. Custom Lambda scanners and metrics duplicate native Control Tower and AWS config compliance capabilities. C. Manually deploying custom config rules is more operationally intensive than activating the managed Control Tower control, and local config events are not automatically centralized by simply creating one event bridge rule in the audit account. D. A scheduled EC2 polling host is higher overhead, slower, and less resilient than the managed compliance notification path. For Control Tower detective controls, look for AWS config-backed compliance plus the audit account notification topics before building custom cross-account alerting. Next, question number 197. A DevOps engineer has implemented a custom AWS Lambda function that programmatically triggers an AWS CloudFormation drift detection operation on a critical infrastructure stack. The engineer configured an Amazon Event Bridge scheduled rule to invoke this Lambda function once every hour. The engineer wants to receive an automated notification via an existing Amazon SNS topic whenever the stack is actually evaluated and found to be in a drifted state. CloudFormation drift detection operations run asynchronously. How can the engineer receive this notification as soon as the drift state is determined? Choices. Option A. Create an event bridge rule that matches source AWS CloudFormation and detail type CloudFormation drift detection status change for the target stack, with detection status complete and stack drift status drifted. Configure the existing SNS topic as the rule target. Option B. Modify the existing event bridge scheduled rule to add the SNS topic as a secondary target. Attach an SNS subscription filter policy to the topic that matches the specific CloudFormation stack ARN to ensure notifications are only sent for the correct stack. Option C. Create a secondary AWS Lambda function designed to pull the CloudFormation API for drift detection results. Configure the secondary Lambda function to publish to the SNS topic if drift is discovered. Add this secondary Lambda function as an additional target to the existing event bridge scheduled rule. Option D. Enable Amazon Guard Duty in the account and configure its CloudFormation drift detection feature. Create a second event bridge rule to intercept Guard Duty finding events related to CloudFormation drift and route these findings directly to the SNS topic. The best choice is option A. Create an event bridge rule that matches source AWS CloudFormation and detail type CloudFormation drift detection status change for the target stack, with detection status complete and stack drift status drifted. Configure the existing SNS topic as the rule target. This works because CloudFormation now sends drift detection status change events directly to Event Bridge. The event includes the stack ID, drift detection status, and stack drift status, so Event Bridge can filter for the completed drifted result and publish to SNS as soon as the asynchronous operation finishes. Now let's rule out the other options. B. The scheduled rule only indicates that the drift detection Lambda was invoked. It does not carry the asynchronous result. C. Polling the CloudFormation API with another Lambda adds unnecessary code and latency now that CloudFormation emits a native Event Bridge drift detection event. D. Guard Duty detects security threats. It does not report CloudFormation stack drift. A helpful shortcut is this. CloudFormation emits native Event Bridge events for drift detection status changes. Filter the completion event instead of polling the asynchronous API. Question number 198. Let's go. This question takes us into managed Prometheus alerts. Scenario. A startup runs a microservices architecture hosted on Amazon Elastic Kubernetes Service, Amazon EKS. The observability team utilizes Amazon Managed Service for Prometheus, AMP, to collect and monitor container metrics. Both the EKS cluster and the AMP workspace reside in the same AWS account. The team wants AMP to evaluate the metrics and automatically dispatch critical workload alerts to an existing Amazon Simple Notification Service, Amazon SNS, topic when container availability drops below a specific threshold. Which combination of steps is required to route these alerts from AMP to the SNS topic? Choose 3. Identify all valid responses. Choices. Option A. Create an alerting rule within the Amazon Managed Service for Prometheus Workspace that defines the mathematical condition for checking container availability. Option B. Configure the Alert Manager receiver block within the Amazon Managed Service for Prometheus Workspace to point to the A or N of the target SNS topic. Option C. Update the resource-based access policy of the target SNS topic to grant the APS, Amazon AWS.com service principal the SNS, publish, and SNS, get topic attributes permissions. Option D. Configure the Amazon Managed Service for Prometheus Remote Write URL endpoint to stream alert payloads directly to the SNS topic ARN. Option E. Modify the IAM execution role associated with the Amazon Managed Service for Prometheus Workspace, granting it identity-based SNS, publish, and SNS, get topic attributes permissions. Option F. Create an OpenID Connect, OIDC, provider for the EKS cluster and associate an IAM role with the Kubernetes cluster service account. Grant this role the SNS, publish permission to authorize the cluster to emit alerts. The correct answers are Option A. Create an alerting rule within the Amazon Managed Service for Prometheus Workspace that defines the mathematical condition for checking container availability. Option B. Configure the Alert Manager receiver block within the Amazon Managed Service for Prometheus Workspace to point to the A or N of the target SNS topic. And Option C. Update the resource-based access policy of the target SNS topic to grant the APS at Amazon AWS.com service principal the SNS, publish, and SNS, get topic attributes permissions. The main reason is Amazon Managed Service for Prometheus, AMP, features a fully managed alert manager. To route alerts to an Amazon SNS topic, 3 configurations must align. An alerting rule must be defined within the AMP workspace to evaluate the Prometheus metrics and actually trigger an alert state. The AMP Alert Manager configuration, YAML, must define a receiver utilizing the target SNS topic ARN. AMP requires authorization to publish to the external SNS topic. Because AMP acts as an AWS service principal, the SNS topic must have a resource-based policy granting the APS, Amazon AWS.com service principal permission to publish messages. Here's why the alternatives are not suitable. D. The AMP remote write URL is designed to ingest metrics into AMP from external clusters. It is not an egress mechanism for alerts. E. AMP relies on the resource-based policy of the SNS topic to grant it access. APS, Amazon AWS.com. There is no specific IAM execution role directly exposed for the AMP workspace itself to modify. F. While IRSA, IAM roles for service accounts, grants permissions to the EKS pods, the alerts are generated and dispatched centrally by the managed AMP service, not by the local EKS pods. Here's a useful exam tip. When integrating Amazon Managed Service for Prometheus Alert Manager with Amazon SNS, ensure you update the SNS resource-based policy to allow the APS, Amazon AWS.com service principal. Next, question number 199. Scenario. A company is refactoring an on-premises internal web application to natively integrate with AWS services. The refactored application needs programmatic access to an Amazon S3 bucket located in a specific AWS account to upload user-generated content. The company insists on using its existing corporate identity provider, IDP, auth.company.com, for application authentication. The corporate IDP strictly supports OpenID Connect, OIDC. A security engineer must architect a solution that grants the web application secure, short-lived access to the S3 bucket. Which combination of actions will establish this secure access? Choose 3. Choose every option that satisfies the requirement. Option A. Create an IAM OIDC identity provider entity in the AWS account utilizing the provider URL, audience client ID, and thumbprint from the existing corporate IDP. Option B. Create an IAM role with a permissions policy allowing the necessary S3 API actions. Set the role's trust policy to allow the newly created OIDC IDP to assume the role, ensuring the string equals condition checks that the auth.company.com AUD context key matches the IDP's application ID. Option C. Configure the application backend to exchange its IDP-issued OIDC token for temporary AWS credentials by calling the AWS STS assume role with web identity API operation. Option D. Configure AWS IAM Identity Center, AWS SSO, by defining a new custom SAML IDP. Upload the SAML metadata XML document extracted from the existing corporate IDP. E. Create an IAM role with a permissions policy allowing the necessary S3 API actions. Set the role's trust policy to allow the OIDC IDP to assume the role, ensuring the condition checks the STS-Amazon.com AUD context key. F. Configure the application backend to utilize the AWS STS GET Federation Token API operation, passing the OIDC token in the request headers to retrieve temporary S3 access credentials. You should choose option A. Create an IAM OIDC identity provider entity in the AWS account utilizing the provider URL, audience client ID, and thumbprint from the existing corporate IDP. Option B. Create an IAM role with a permissions policy allowing the necessary S3 API actions. Set the role's trust policy to allow the newly created OIDC IDP to assume the role, ensuring the string equals condition checks that the auth.company.com AUD context key matches the IDP's application ID. And option C. Configure the application backend to exchange its IDP-issued OIDC token for temporary AWS credentials by calling the AWS STS Assume Role with Web Identity API operation. Let's look at the reasoning. To establish secure web identity federation using an external Open ID Connect OIDC provider, AWS requires a three-step architecture. Establish trust by creating an IAM OIDC identity provider in the AWS account, mapped to the corporate IDP. Create an IAM role trusting that specific IDP entity. The trust policy must use a condition checking the audience claim, issuer on URL AUD, to prevent token substitution attacks. The application logic must dynamically exchange the JWT/OIDC token issued by the corporate IDP for short-lived AWS credentials by calling Assume Role with Web Identity. The other choices do not work because D. AWS IAM Identity Center, formerly AWS SSO, is optimized for workforce access to AWS consoles and CLI tools, not typically for internal application-to-service programmatic federation flows via standard OIDC token exchange. E. The trust policy context key for an OIDC provider is constructed using the issuer URL, for example, auth.company.com AUD, not the generic STS-Amazon.com AUDF. Get Federation token is used when a pre-authenticated IAM user needs to then scope temporary credentials to a subordinate user or application. It is not the API used for OIDC JWT Web Identity Federation. Keep this point in mind for the exam. Web Identity Federation for applications always involves creating an IAM OIDC identity provider, a trusting IAM role mapping the issuer EUD key, and calling the Assume Role with Web Identity STS API. Question number 200. An enterprise is in the middle of a hybrid cloud migration. They currently build and package internal software libraries using a legacy CI/CD pipeline running entirely on bare metal servers in their on-premises data center. The engineering team is adopting AWS Code Artifact. They want to securely publish their internally built software packages to Code Artifact, while also utilizing Code Artifact as a proxy to fetch dependent public libraries, for example, from NPM.js or Maven Central, for future cloud-native pipelines. Which combination of steps configures this architecture with the least operational overhead? Choose 2. Identify all valid responses. Options. Option A. Implement AWS IAM roles anywhere by establishing a trust anchor. Create an IAM role trusting the anchor with permissions to publish to Code Artifact. Update the on-premises CI/CD pipeline to use its local certificates to assume this role and push packages directly to Code Artifact. Option B. In one Code Artifact domain, create a dedicated proxy repository for each required public registry, with one supported external connection on each proxy repository. Configure the application-facing Code Artifact repositories to use the required proxy repositories as upstreams. Option C. Generate a long-lived Amazon S3 pre-signed URL granting S3. Put object permissions. Modify the on-premises pipeline to upload compiled packages to an S3 bucket via this URL. Deploy an AWS Lambda function triggered by S3 uploads to push the packages into code artifact. Option D. Package the CI/CD build outputs into a virtual machine image. Use the AWS VM import export service to convert the image into an Amazon EC2 AMI. Launch the AMI with an IAM instance profile and use a user data script to publish the internal packages to code artifact on boot. Option E. For every required public repository, for example, npm.js, Maven, create a separate downstream code artifact repository. Individually link each of these downstream repositories directly to the on-premises build server using VPC endpoints. The answers that work here are Option A. Implement AWS IAM roles anywhere by establishing a trust anchor. Create an IAM role trusting the anchor with permissions to publish to code artifact. Update the on-premises CI/CD pipeline to use its local certificates to assume this role and push packages directly to code artifact. And Option B. In one code artifact domain, create a dedicated proxy repository for each required public registry, with one supported external connection on each proxy repository. Configure the application-facing code artifact repositories to use the required proxy repositories as upstreams. IAM roles anywhere allows the on-premises CI/CD servers to obtain short-lived AWS credentials from X.509 certificates and publish directly to code artifact without long-lived access keys. For public dependencies, a code artifact repository can have only one external connection, so use one proxy repository per public registry and make those repositories upstreams of the application-facing repositories. This preserves centralized caching and a single client-facing endpoint per application repository. C. S3 pre-signed uploads plus Lambda forwarding add unnecessary storage, code, and asynchronous processing when code artifact accepts authenticated publishing directly. D. Importing a build server as an AMI merely to publish packages is slow and operationally excessive. E. VPC endpoints do not solve package source topology, and creating a separate application repository for each public registry is unnecessary because an application repository can use multiple code artifact upstream repositories. Exam tip. A code artifact repository supports only one external connection, but up to multiple upstream repositories. Use one proxy repository per public registry and aggregate them through upstream relationships. Next, question number 201. A company is developing an application that generates high-frequency log events. The log events produce a large amount of telemetry data, emitting 5 distinct performance metrics every 1/10 of a second. The company needs to configure the application to write these logs to Amazon TimeStream. A data analytics team will configure a daily query against the TimeStream table to monitor system performance. A DevOps engineer must optimize the data ingestion and storage architecture. Which combination of steps will meet these requirements and provide the fastest query performance? Choose 3. More than one answer may be correct. Option A. Use batch writes to ingest multiple log events in a single write operation. Option B. Write each log event immediately as a single write operation. Option C. Format and ingest each log event as a single measure record. Option D. Format and ingest each log event as a multi-measure record. E. Configure the memory store retention period to be longer than the magnetic store retention period. F. Configure the memory store retention period to be shorter than the magnetic store retention period. The required selections are Option A. Use batch writes to ingest multiple log events in a single write operation. Option D. Format and ingest each log event as a multi-measure record. And Option F. Configure the memory store retention period to be shorter than the magnetic store retention period. Here's why. To optimize Amazon TimeStream for high-throughput ingestion and fast querying, batch writes A. should be used instead of single writes to reduce network overhead and improve throughput. Because the application emits 5 distinct metrics at the exact same timestamp, every 1/10 of a second, using multi-measure records, D. allows all 5 metrics to be stored in a single row. This drastically reduces data volume and accelerates query performance. Finally, TimeStream strictly requires the memory store retention period to be shorter than the magnetic store retention period, F, as memory is optimized for short-term, fast point-in-time queries, and magnetic is used for cost-effective long-term analytics. The remaining options can be eliminated because B Single writes introduce massive network overhead and API latency for high-frequency logs. C. Single measure records would require 5 separate rows/writes per timestamp, increasing storage footprint and severely slowing down analytical queries that need to correlate the metrics. E. Configuring the memory store retention period to be longer than the magnetic store retention period is structurally invalid in Amazon TimeStream. Memory retention must be shorter. The main takeaway is when using Amazon TimeStream for telemetry or logging, always use multi-measure records for metrics emitted at the same timestamp and utilize batch writes to maximize performance and minimize cost. Next up is question number 202. We're moving on to EC2 credential source binding. A company operates sensitive Amazon EC2 workloads in one AWS organization's OU. Each instance receives temporary credentials from a unique IAM role through an instance profile. The workloads access AWS services through VPC endpoints, so request context includes the originating VPC and VPC source IP. The security team wants an organization-wide control that prevents exfiltrated EC2 role credentials from being used from a different VPC or from a different private IP version 4 address, while allowing AWS services to make legitimate calls on behalf of the instance role. Which SCP configuration will successfully enforce this restriction? Review the options. Choice A. Apply an SCP to the OU with separate deny statements for EC2 instance role sessions. When EC2 source instance ARN is present and AWS via AWS service is false, deny if AWS source VPC does not equal $AWS EC2 instance source VPC and deny if AWS VPC source IP does not equal $AWS EC2 instance source private IPv4. Choice B. Apply an SCP that allows the credentials from any private IP version 4 address inside a hard-coded production VPC CIDR, regardless of the instance that originally received the credentials. Choice C. Maintain static organization-wide lists of permitted VPC IDs and private IP addresses and compare requests only with those lists. Choice D. Compare AWS EC2 instance source VPC with AWS VPC source IP and compare AWS EC2 instance source private IPv4 with AWS source VPC in a deny statement. The answer here is option A. Apply an SCP to the OU with separate deny statements for EC2 instance role sessions. When EC2 source instance ARN is present and AWS via AWS service is false, deny if AWS source VPC does not equal $AWS EC2 instance source VPC and deny if AWS VPC source IP does not equal $AWS EC2 instance source private IPv4. This is the best choice because AWS supplies AWS EC2 instance source VPC and AWS EC2 instance source private IPv4 for credentials delivered to EC2 instance roles. Comparing those credential origin values with the request's AWS source VPC and AWS VPC source IP binds direct credential use to the original VPC and private address. Testing EC2 source instance RN scopes the policy to EC2 role credentials and excluding AWS via AWS service calls avoids blocking service-to-service requests made on behalf of the instance. Let's quickly check the incorrect choices. B. A VPC CIDR only binds credentials to a broad address range, not to the specific instance that received them. C. Static VPC and IP allow lists are brittle and do not dynamically bind each credential session to its issuing instance. D. It compares a VPC identifier with an IP address and an IP address with a VPC identifier, so the condition logic is invalid. To reduce EC2 role credential exfiltration risk, compare the request source VPC/private IP with the EC2 credential origin context keys and account for AWS via AWS service. Question number 203. Let's go. Scenario. An engineering team maintains a production REST API built using Amazon API Gateway and AWS Lambda. The team relies on AWS Code Pipeline and AWS Code Deploy to orchestrate updates. During the last few releases, bugs in the new code caused widespread HTTP 502 bad gateway errors for end users before the team could manually intervene and roll back the deployment. The engineering manager mandates a new automated deployment strategy. The solution must automatically detect API errors and revert to the previous stable version immediately. Crucially, the deployment must initially expose the new version to the smallest possible percentage of customers to limit the blast radius. Which deployment strategy and rollback configuration meets these requirements with the most operational efficiency? Choices. Option A. Create a custom code deploy Lambda Canary deployment configuration that shifts 1% of traffic in the first increment and the remaining traffic after a monitoring interval. Attach a CloudWatch alarm for API gateway HTTP 502/5xx errors to the deployment group and enable automatic rollback. Option B. Use the predefined Lambda Canary 10% 10 minutes configuration with the same CloudWatch alarm and automatic rollback settings. Option C. Create a custom 1% Canary deployment configuration, but use a CloudWatch logs metric filter and a custom Lambda function to call code deploy APs for rollback instead of enabling code deploy automatic rollback. Option D. Use Lambda all at once with a CloudWatch alarm and automatic rollback. The right response is Option A. Create a custom code deploy Lambda Canary deployment configuration that shifts 1% of traffic in the first increment and the remaining traffic after a monitoring interval. Attach a CloudWatch alarm for API gateway HTTP 502/5xx errors to the deployment group and enable automatic rollback. This works because code deploy supports custom Lambda Canary configurations with a first traffic increment from 1% to 99%. A 1% canary minimizes the initial blast radius. Code deploy deployment groups can monitor CloudWatch alarms and automatically stop and roll back when an alarm enters alarm, so no custom rollback function is needed. Now let's rule out the other options. B. A 10% canary is safer than all at once, but does not satisfy the requirement to expose the smallest supported percentage first. C. The 1% traffic shift is appropriate, but custom rollback code is unnecessary operational overhead because code deploy supports alarm-driven automatic rollback. D. All at once exposes every customer to the new version immediately. A helpful shortcut is this. Code deploy Lambda canaries can be custom. Use a 1% first increment when the requirement is the smallest supported blast radius, and pair it with CloudWatch alarms plus automatic rollback. You have completed set 11 of the DOP-C02 AWS Certified DevOps Engineer Professional Practice Question Series. How did you score? Share your result in the comments. Work through all the sets to build broader exam readiness and cover more practice questions. Please like this video, subscribe to Tech with Kaushik, and enable notifications for more certification exam preparation content. Thank you for watching, and I will see you in another practice set.